Hello and welcome back. Let us try to understand some linear algebra. As part of this, we are going to explain linear dependence and linear independence of vectors, and then we are going to understand rank of a matrix, and then we are going to understand a little bit on vector algebra. And the ultimate goal of this session is to explain you and make you understand what is eigenvectors, eigenvalues, and singular value decomposition. Because these two concepts, the eigenvalues, eigenvectors, and singular value decomposition, is used in many places in machine learning and deep learning. So understanding these concepts is very crucial, and the fundamentals for these two concepts are whatever we are covering here. And we covered some of the linear algebra in previous sessions. They also add up here, and let us start. Let us start with linear independence and linear dependence of vectors. So if you take v1, v2, and so on, vn vectors, and you have to say them, you have to tell them that these vectors are linearly independent. Only way is that you take an equation a1 v1 plus a2 v2 and so on, a and bn is equal to 0. This is true only when a is equal to 0. All coefficients are 0, then only it is 0. No other coefficient can make the linear combination of vectors 0. Any number in this equation multiplying one of the vectors and making it 0 makes the vectors dependent. Linear combinations of vectors is equal to 0 only when the coefficients are 0. That is linearly independent. If you want to simply understand as a layman, if you look at these two vectors, v1 is 1, 2, 3 and v2 is 2, 4, 6. You can clearly see that v2 is equal to 2 into v1. Right? If the vectors are like this, right, then we can say they are dependent. Right? If you actually say v2 plus minus 2 into v1 is equal to 0, right? v2's coefficient is 1, v1's coefficient is minus 2. A linear combination where coefficients are non-zero and we are able to generate a linear combination of these two vectors as 0, so the vectors became dependent. Simply understanding, if you see any two vectors and you can multiply with some number and generate other vector, those two are dependent vectors. In our statistical terminology, we say these are strongly correlated. The correlation is 1. The one is increasing, the other is also increasing, right? So in linear algebra we call it as linear dependence. Okay, linear dependence and strong correlation are one and the same. Okay, so linearly independent, if you look at these two vectors, right, you cannot generate one vector by multiplying with any number on the other vector. So they are linearly independent. Simply understanding, if you can multiply with some number and generate other vector, then they are dependent. If not, they are independent. Okay, so let us try to see how mathematically you can find out the whether two or more vectors are linearly dependent or not. So I have taken 3 independent vectors. I already know because I derived it, so I already know. So I have taken 3 vectors, each vector of dimension 4. When I say a vector of dimensionality 4, that means it's a one column with 4 values. Okay. In a matrix, if you want to say a dimensionality, you will say m by n, m rows and n columns. But in a vector, you say dimensionality, which is nothing but rows only, because you will have one column, right? So these are vectors of dimensionality 4, we can say. This terminology, right? You need to remember. These are vectors of dimensionality 4. I have taken linearly independent vectors. So let us see whether they are independent or not. So I am going to form a linear equation and see whether all coefficients are going to be 0 to make the linear combination 0. To do that, what we need to do? We need to take a linear combination and make it 0 and see what these coefficients are, or derive what these coefficients are. So to derive those, we need to form equations like this. We can actually form equations a1 into 1 plus a2 into 0 plus a3 into 2 is equal to 0. a1 into 2, right, plus a2 into 1 plus a3 into 0 is equal to 0. Like that you can form 4 equations because each vector is of 4 dimensionality. Okay, so now we need to solve these equations. I think you have you know how to solve equations We have studied that in our 8th standard, 9th standard level. So let us look at it. So here what I did is I took the second equation and the third equation. If you look at the second equation, 2a1 1a2 plus 0a3 is equal to 0, and the third equation is 1a1 plus 1a2 plus 1a3, and we solved those two equations. To solve them, I subtracted one from the other. From second equation I subtracted third equation to eliminate one variable there. So we are trying to find these variables a1, a2, a3. So I have got an equation with a1 and a3 which is equal to 0, because the target output, the right hand side is 0, right? So I have taken the fourth equation and third equation. I am subtracting third equation from fourth equation so that I can eliminate a2 on that equation also. So when I have two equations which are of a1, a3, I can solve those two and generate, I can find out one value. So out of this solution, I subtracted third equation from fourth equation. I have got 3a1 plus 6a3 is equal to 0. Now if you multiply this equation with 3 and subtract it from this equation, you get a3 value. See this here, 3a1 plus 6a3 is this output, and 1a1 minus 1a3 is this output, and I am multiplying this with 3 and then subtracting it one from another, and I have got 9a3 is equal to 0, a3 is equal to 0. I have got one coefficient 0 of the linear combination of three three vectors. One coefficient I have got 0. If I substitute this value into one of the equations, right, I may be able to find a1. The equation is first equation. If you look at first equation, 1a1 plus 0a2 plus 2a3 is equal to 0. If I substitute a3 is equal to 0, I am getting a1 is also 0. So two coefficients are 0. When I substitute a1 and a3 and a1 into the second equation, I am getting a2 also 0. All three coefficients are 0. The linear combination of three vectors are becoming 0 only when the coefficients are 0. That means these three vectors are linearly independent. Okay, if you look at this, found a1, a3, a2, a3 is equal to 0 after solving equations. Hence v1, v2, v3 are linearly independent vectors. They are independent vectors. Okay, so let us take one more example of linear dependent vectors. I have taken three vectors which are linearly dependent. Let us see. In mathematics, how do you find whether three vectors are linearly dependent or independent? That's what I am trying to explain here. Okay, so when I solve these three equations, right, I found equations. When I solve these three equations, I have got a2 is equal to minus 5a3 by 8 and a1 is equal to minus 1a3 by 2. Okay, when I substitute a3 is equal to 1, I got a1 is equal to minus 1 by 2 and a2 is equal to minus 5 by 3. That means when I take, when I have non-zero coefficients for the linear combination of these three vectors, they are becoming 0. That means you can multiply, two equations with some numbers and subtract it from another equation and you get 0. So that means you can generate one vector based on other vector, or maybe using multiple vectors you can generate one vector. That means they are linearly dependent. One is dependent on other. You can generate one from the other, right? So that is linearly dependence. So let us try to understand. We understood linear dependence and linear independence of vectors. Now let us try to understand a little more properties about the linearly independent and linearly dependent vectors. Basic concept is that if a vector has got all zeros, right, then it is called a zero vector. At least one number is non-zero, then the vector is called as non-zero. If you look at these, right, these three vectors are non-zero vectors because at least one number is non-zero. Okay. So if a set containing a zero vector is always dependent, that's one property of the vectors. If you look at these, this example, right, 0, a1, a2, three vectors are there. If you want to make a linear combination, even if you are multiplying a1 and a2 with 0, some number can multiply the zero vector so that you can make the linear combination 0. When you make linear combination 0 by having at least one coefficient non-zero, the vectors become independent. We have seen it, right? If you make a linear combination of vectors and at least one coefficient is non-zero, then the set becomes dependent vectors. So because of the zero vector it became. So if a set of vectors have got a zero vector, then the set is linearly dependent. That is one property. A set containing m number of n by 1 dimensional vectors is linearly dependent if m greater than n. See this here? We have 4 vectors. Each vector is of size 3. So here m number of vectors are there. M number means 4. And then the dimensionality of each vector is n by 1, right? 3 by 1. So 4 is greater than 3. So these are linearly dependent. Now in a matrix, if number of columns are more than number of rows, right? You can say the matrix is of dependent vectors. Okay. So if a set of vectors are linearly independent, then removing one arbitrary vector from the set will not make any effect. If you took 3 vectors and they are linearly independent, if you take out one, right, still the rest of the 2 are going to be linearly independent only. If you add more, right, we don't know. It may become linearly dependent or independent, depending on the additional vector. By chance, if you add a if you multiply one vector with some number and add it to the set, right, it becomes dependent, right? So when you remove one vector from linearly independent set of vectors, it's not going to affect the existing whatever n minus 1 number of vectors, the linear independence. Okay, and a set containing unit vectors is linearly dependent. When I say unit vector, right, the vector's length is 1. We can calculate vector's length and we'll see it. We'll see it in a coming one of the videos. We'll see that. So vector's length is calculated using square root of this square, first value square plus second value square plus third value square. That is the length of a vector. If you do that, right, it is 1 square, square root of 1 square plus 0 square plus 0 square. That is square root of 1 square is 1. So unit vectors, these 3 vectors are unit vectors. A set containing distinct unit vectors. Sometimes when you have other values also, the vector becomes a unit vector. We have some number here, some number here, and some number here. Then also the vector becomes a unit vector. If that kind of vectors, unique distinct vectors are there, then set of those unique, the unit length vectors are linearly independent. So we have understood the concept of linearly dependence and linear independence so far. And in coming session, we will understand what is rank of matrix and how to calculate rank of a matrix. In that session, right, we will understand how to solve equations using row reduction echelon form. Thank you.